Okay, so of course we need to have rules that make taking derivatives easy when we're working with vectors. Now here's the key. So the main ones are the main rules are chain rule that deals with the composition of functions. Now remember, this is going to be vector valued functions, right? And that's the same as scalar valued. And now for product rule, things get a little weird because we've got three different ways to multiply. So you can have a scalar times a vector, right? You can have a vector dotted with another vector, and you could have a vector crossed with another vector, right? So we have quite a few rules because we've got quite a few different ways to multiply. So in all three of those deal with the product rule. Guess what we don't have? We don't have a quotient rule because we don't really divide a vector, right? You can't divide R of t over S of t. Doesn't make sense. So that would be like, what? We don't divide vectors. Okay, so no quotient rule. Okay, let's get to it. So in what follows, C is a scalar, which means just a constant, right? Constant real number. And U and V are differentiable vector functions. And remember, in order to be differentiable, that means that the limit as h approaches 0 of r of t plus h minus r of t over h, this has to exist, right? Okay. And then lastly, f is a real valued function. So, like f of x. Okay. Okay. So here are our differentiation rules. First one should be pretty reasonable. If you want to take the derivative of the sum, it's just the sum of the derivatives. If you have a scalar multiple, you can just pull the scalar out front. Okay. And if you have a scalar function and it's being multiplied by a vector, then we've got our old-fashioned product rule. So it's just of the scalar times the vector plus the scalar times the derivative of the vector. If you're going to do the dot product of two vectors and the derivative, then you just are going to the dot the derivatives, basically. So this is pretty similar. You're going to, as our other uh, formula, but remember you're just using dot product now. Now the last one is the last one involving product rule, because this is product, excuse me, this is a product rule, this is a product rule, this is a product rule. Technically speaking, this is also a product rule because your function f of x could just be a constant c, right? So you could just have c, right? And in that case, when you take f prime of x, it'll just be equal to 0. So you would have 0 times u plus c times u prime, right? So 2 is a little redundant. 2 is a special case of number 3, but that's okay. The thing I want to note for P is that the order matters. Okay? So remember that U, what was it like? U cross V is going to be negative V cross U. Do you remember that? So here, if you are taking the derivative of U cross V, make sure that you are doing U prime cross V plus U cross V prime. Whereas for the dot product, order doesn't matter because taking the dot product is commutative. Doesn't matter. And lastly, we have our chain rule, which is if you have, this is first you're applying U, sorry, first you're applying F and then you're applying U, right? This is going to be the derivative of that with respect to t is going to be F prime times U prime of F. Okay. All right. So to prove the theorems, you can use the definition one, which is the definition one is this definition right here, where you're looking at the quotient, the limit quotient of the difference quotient, limit of that difference quotient. Or you could use theorem two, which talks about taking derivatives component by component. Because, for instance, if you know that you can write U, say, for instance, if you can just write U as FGH, okay, now you've got some scalar. So let's see here. So let's just show you with number 3 here. Okay, so number 3, we're going to say imagine U of t. We'll have U1 of t, U2 of t, and U3 of t. Okay, and f of t is a scalar valued function. And we want to know what is the derivative of f of t, u of t. Well, the first thing we can do is we know that multiplying f of t times u of t is going to happen component-wise. So we've got f of t, u1 of t, f of t, u2 of t, f of t, u3 of t. Okay, so we're looking for the derivative. Does that make sense? We're just rewriting f times u in terms of components. And now we know that taking the derivative, according to theorem 2, is the same as just taking the derivative in each component. So we'd have f u1 prime, f u2 prime, f u3 prime, right? And then in each one, what will you have? You'll have, let's see here, let's compute here. So we're just doing for formula 3. So then we would have, so we need f, so we have f u1 prime in the first component, f u2 prime, and in the second component, and f u3 prime in the third component. Now, the derivative of f u1 is just our regular product rule from calculus 1. So that'll be f prime u1 plus f u1 prime. And the same for the second component, f prime u2 plus f u2 prime. And the third component, f prime u3 plus f u3 prime. Now we can take these and split them up into f prime u1, comma, f prime u2, comma, f prime u3 plus, so I did that one, that one, that one. What's left over? F u1, f u2, f u3. Okay? And now we can factor out the f prime from the first vector. So we'll get f prime times u1, u2, u3. And from the second vector, we can factor out an f u1. Those should have primes. u1 prime, u2 prime, u3 prime. But now, look, this is the same. That's just u, right? So f prime u plus, and that is u prime, fu prime. Okay? So fu prime is f prime u plus f u prime. Okay, and that just shows you how to use the fact that derivatives are component wise in our previous uh, differentiation formulas for calculus one, from calculus 1 to verify these 6 rules. Okay. All right. Let's just look at one example where we're using the properties of or using the differentiation rules. So here we have an example. Show that if the length of r of t is a constant, then r prime of t is orthogonal to r of t. Okay, so here's the deal. So we want to say that if the magnitude of r of t is some constant, then r prime of t is orthogonal to r of t. And this is true for all t. Now, first of all, what does it mean, or what's one way that we can prove that r prime of t is orthogonal to r of t? Well, this happens if the dot product is equal to 0. So another way of writing this is to say that we want to say that r of t dotted with r prime of t is equal to 0. Okay? Now, let's work on the front half here. What does it mean to say that the magnitude of r is constant? Well, remember that the magnitude, right, so remember that the magnitude of a vector is the square root of the vector dotted with itself. Do you remember that? So the magnitude of u is equal to the square root of, say, u1 squared plus u2 squared plus u3 squared, right? But that's just the square root of u1, u2, u3 dotted with u1, u2, u3. Does that make sense? So if the magnitude is constant, that means that the square root of r dotted with itself is some kind of constant. So that means that r dotted with itself has to be a constant, right? Because of constant squared, right? If we square both sides here. So r dotted with r is a constant squared. That's just another constant. So not necessarily the same constant. You get what I'm saying here? It's just another constant. So what does it mean for r dotted with r to be a constant? Well, that means that the derivative has to be equal to 0. Does that make sense? So let's put up here that if the magnitude of r is constant, then the derivative of r dotted with itself has to be equal to 0. And now we should have some properties. Let's go to our differentiation rules. This is the formula. So we're going to apply this formula with r of t dotted with r of t. It's going to be r prime of t dotted with r of t plus r of t dotted with r prime of t. So that's just going to be 2 times r dotted with r prime, right? So if r is constant, that implies that d dt of r dotted with r is equal to 0. Okay, but that means that 2 times r dotted with r prime is equal to 0. We divide both sides by 2. That means that r dotted with r prime is equal to 0. And that means that r is perpendicular to r prime. And the geometric analysis of this example is that if a curve lies on a sphere with the center at the origin, then the tangent vector is always perpendicular to the position vector. So if you've got some curve here, right, and the curve lies on the sphere, then the tangent vector is always perpendicular to the position vector. Okay? Because what does it mean for the curve to lie on a sphere with center the origin? That means that the length is constant, right? Then the tangent vector is always perpendicular to the position vector. That's the second half here. R prime is orthogonal to R. Okay.